Okay, from our very short acquaintance with scalar functions of two variables, I hope you've already been convinced that they're not going to be easy to draw. Okay, so I want to remind you, the domain is in the xy plane. The graph of the function of two variables, only two variables, is some surface lying up here, or underneath the xy plane. It could be negative, of course. Okay, so everybody grasps that already, right? So, well, the topic of our discussion now, called level curves, is another approach to trying to understand functions without being able to draw their graphs. And in fact, this is something you all know. This is something you've all seen. And what do I mean? So think of the function that in every given point, xy, on Earth, think of Earth, big Earth. For any given point xy, well, Earth is round, but let's think we're living like several hundred years ago and we still think it's flat. So on every point xy, the function gives you the height of land at that point. Okay? So if you're on a big mountain, the function is going to give you, let's say, 5,000 meters, or translate that to feet, whatever you're used to. And if you're on a little hill, it's going to be maybe 200 meters, like here in Haifa. Or if you're at sea level, it's going to be 0 meters. Okay? The function gives you at every point the height of Earth's surface at that point. Okay? Now you want to go on a trip. Usually what you take with you, well, you're hiking out there. You don't have your computer and all the fancy programs that today exist. You have a map. What does the map show you? Well, the map shows you something called topography, or a topographic map, and it shows you these lines. Okay, maybe something like this, and then maybe something like this. Do you all know what I'm talking about? Do you know what I'm trying to draw here? Okay, and maybe something like this. And what do these lines stand for? Well, this is the line. Let's say on the map it says 100. So these are all the points where the height of the mountain, this is an aerial view from bird's eye view of the surface. And all the points here, these are all points xy, where the mountain is exactly 100 meters high. And then let's say if this is 200, then these are points where the mountain is 200 meters high. And this may be 300, and that's the peak of the mountain. And then maybe this is 0. And if this is 0, then you might expect the map to be colored with blue here to indicate that this is what? Some sea or ocean or pond or lake or whatever at sea level. So does everybody know what I'm talking about? Okay. So note that this is only a drawing of the xy plane, the domain of the function, but it still captures information about the function itself, about the height at every point. Okay, is this clear? Okay. These lines are called level curves. Okay, that's what they're called, level curves, and I'm going to write a formal definition in a second. And in particular, you can already notice that a level curve, which is going to be all the points where the value of the function is fixed, is not always a curve. So for example, all the points where the value of the function is 0 is not exactly a curve. It's actually a big surface. Do you see that? Okay, a big chunk, a big area. Do you see that? Okay. So let's write the formal definition and then do some examples. So I'm going to move over to this board here and write the definition. So it's going to be a curve. We're going to define it as a curve, although we remarked that it's not necessarily a curve. So a curve, and we're going to call it L, a curve L, in the xy plane, which is the domain of our functions, is called a level curve of fxy if the value of f on every point of L, this level curve, is some fixed constant c. Okay, so this is the definition of a level curve, and just a remark, it's not necessarily a curve. So it's kind of a weird remark, but that's the terminology. So points where fxy is a constant, so if you take all the points where some function gives you a constant value, are not always, strictly speaking, a curve. They could be an area. Okay? So is this clear? So let's do an example. So the first example I want to do is going to take us back to a function which we've already seen. Look on this board. So this function, the function fxy equals x squared of y squared, is an example where we already know how the graph looks. Okay, so the graph of this function is this paraboloid. We discussed this previously. Okay, what would the level curves of this function look like? So remember, when I'm drawing this, the xy plane is down here. Okay, I'm doing this, but it's actually flat. And the graph is up here, right? When I'm drawing level curves, I'm only drawing an aerial view of the xy plane. So here's the xy plane now. Now I'm drawing it, looking at it from above. This is the map I'm holding when I'm walking on my hike. And what are all the points, for example, where this function has a value of 0? Right. Only at this point, the function has a value 0. Do you agree? What are all the points where this function has a value of 1? Right, it's a circle of radius 1. Do you agree? On all the points of radius 1, which look like this, so this is 1 here, the value of that function, which is going to live up here, I'm doing up but moving towards you, because now it's an aerial view of the domain, right? So over here lie all the points whose function's value at is 1. Do you agree? So this corresponds to the constant c equals 1. This is the level curve corresponding to the constant c equals 1. Do you agree? Do you agree that if I take now a circle of radius 2, so this is a circle of radius 2, what would be the value of all the points, the value of the function, calculated at all the points on this circle of radius 2? X squared plus y squared. 4. Do you agree? So this is the level curve corresponding to the constant c equals 4. On all these points, the value of the function is 4. Does everybody see that? And if I take now the circle c equals 3, the circle of radius 3, this corresponds to all the points where the value of the function is 9. Do you see that? Okay? So if I use my imagination now, and if this is what I see on my map, I can imagine this crater, this round crater, whose bottom is at 0, this corresponds to c equals 0, and as you go outwards, it rises. So I can, looking at this, I can imagine that. Do you see the correspondence? Okay? And the advantage of this over that is that that is three-dimensional. That's harder to draw. And this is two-dimensional. It's easier to draw. Okay, clear? I want to do another example, but this time I'm going to give you a formula for the function without knowing what the graph looks like. We're going to decipher from the formula the level curves and then try to understand what the function actually looks like, what the graph looks like, without knowing it in advance. Okay, so here's another example. So let's look at the function f of xy equals x times y. Nothing too sophisticated. X times y. And let's see what we have. So here's, again, just the xy plane, and I'm only going to draw the level curves. Okay, this is just the domain of the function. What is the domain, by the way, of this function? Where is it defined? Right, it's defined everywhere. It's defined for any x and y, right? Okay, so what am I trying to figure out? For example, for which values, when is x times y equals to 0? For which values of x and y is x times y equals 0? Is the function equals to 0? Okay, so when can this product be 0? If and only if x is 0 or y is 0. Do you agree? So the level curve corresponding to the constant c equals 0 is the axes. Any point on these axes has either x or y as 0, and therefore any point on these axes, the value of the function would be precisely 0. Do you agree? So this is where the function hits the floor. Do you see that? Okay, so these two correspond to c equals 0. This line and this line. Does everybody agree? Clear? When is xy, so let's write that, xy equals 0 if and only if x equals 0 or y equals 0. When is xy equal to 1? When is the product of x and y equal to 1? I'm just going to rewrite that. That's going to happen when y is 1 over x. Do you agree? Right? I know how to draw this. I know how points that satisfy that the y is 1 over x, I know how to graph them. This is a calc 1 function, right? This is a function of y variable. It's written as y as a function of x, right? So all the points here along this hyperbola here, this is y equals 1 over x. Do you agree? And all these points correspond to points where the function is valued 1. Do you see that? So along these points, the value of the function is the same. On all these points, the value of the function is precisely 1. Clear? And we can continue this. When is xy equal to 2? If and only if y equals 2 over x. Y equals 2 over x is again a hyperbola looking like this, but somewhat further from the origin. So these two lines correspond to c equals 2. Okay, and you can see that it goes on. So c equals 3, c equals 4, right? What about negative values? When is xy going to be equal, for example, to negative 1? So that's going to happen when y equals negative 1 over x. I know how to draw that as well. Negative 1 over x looks like this. This is negative 1 over x. Do you agree? So these are the points where the value of the function is negative 1. On all points xy in the plane living along these two curves, the union of these two curves, the value of the point satisfy this relation, therefore this relation, therefore the value of f on these points is negative 1. Okay? It's under the board. If this is the floor, the graph is under the board. Do you see that? Okay? And likewise, xy is going to be negative 2 if and only if y equals negative 2 over x. And those are going to look like this. So these are the points where the value is negative 2. Okay? Now at this point, I can already picture the graph. I can understand if somebody gave me this and told me, here's your topographic map, what would you see if you stood here and looked at the mountains? What's the phenomenon? What's the graph going to look like? Well, let's think for a minute. As I go further, deeper into the first quadrant here, these are mountains that are rising. Do you see that? Does everybody see that? 1, 2, and here there's going to be a level curve of 3 and 4. So think of an aerial view and now put it on the floor. If I go into the first quadrant, I'm going up. Likewise, if I'm going deeper into the third quadrant. Okay, so if let's do it like this. Here I'm going up. Do you understand what I'm doing? Why I'm doing up? Okay, you're doing it too. Great. I'm going up, and here I'm going up as well. Do you see that? Okay, so both here and here, I'm going up. As I go further out into the first and the third quadrants. Do you see that? As I go further out into the fourth and the second quadrant, I'm going down. Well, I can't do that. I can't point into the board, but what I'm doing is going down, further down. Do you see that? So can you tell me what you're seeing here? Exactly. Very good. What we're looking at is the graph of a function that looks like a saddle. Okay? We're going up here, and we're going down here. Okay? So fxy equals xy, the graph of this function is a saddle. Okay? Told you it's not going to be too easy. Okay, not going to be too easy, but raise your hand if you see this. If you see the correspondence between this function, these level curves, and this conclusion here. Raise your hand. I want to understand how many people are with me. Very good. Oh, okay. So is there anybody that didn't raise his hand? Well, you came in late. So I'm not going to ask you. Okay, so when we drew a saddle, okay, when we had this example, do you remember what the formal name of a saddle was? Pringle. Okay, no, that wasn't the formal name. Okay, so remember that the paraboloid that we just drew a couple of boards ago was called an elliptic paraboloid because it was the shape of a paraboloid, but the cross sections were always ellipses. Okay, and in fact, the one that we drew, these ellipses were circles. And a saddle we called a hyperbolic paraboloid because it's made of two parabolas. Remember the two parabolas like this, but the sections are hyperbolas. These are these hyperbolas here. Okay, so it's called a hyperbolic paraboloid. That's the formal name of a saddle. And the one we drew, so this is just a remark, we met a different saddle. The one we met was z equals x squared minus y squared. And it's, in fact, one can, it's not easy to see, not with the tools that we have now, but these two are just rotation. One is the rotation of the other. So this one had so this one, the one we drew now, has the axes as the points where the value is 0. Okay? And this one, x squared minus 1 squared, had y equals x and y equals negative x. This cross like this as the points where it's 0. And then the hyperbolas looked like this and like that. Okay? So if you're wondering how the two relate to each other, that's how they relate to each other. Okay? Is it clear what level curves are and how they kind of show us, kind of help us understand the function clearly in a more challenging way than being able to draw the graph. When you're able to draw the graph, that's more illuminating. You can understand the function better, but we can still get a lot of information from looking at pictures like this. And it takes practice. Okay? Okay, so what I want to do next is to do the almost impossible and try to understand functions, scalar functions, where the domain is R3, functions of 3 variables. Okay? And we're never going to be able to draw those. That's going to be way too difficult because that's going to require 4 dimensions. And man, I'm 1 dimension short of that. But we're going to be able to do something similar to these level curves, which is going to help us understand them. That's coming up next.